And just as a slight extension of what we were doing in the last question, instead of talking about two parallel wires, we can have a wire and a charge that moves parallel to it. So instead of using IL cross B for my force, I have QV cross B. Again, that field, we're going to use this very common result, where in this case, the distance over here is 0.2 meters, and we have the current already. So this, using the right-hand rule, we find that the magnetic field created by this current is going to be pointing out of the page wherever my charge is currently flowing. That force is given by, of course, QV cross B. And again, theta as you go to 9 degrees, so we can just say that the magnitude of the force is QV times B, without the sine theta part. To get the direction, by the right-hand rule, of course, this is a moving negative charge, so you gotta put your QV direction opposite to this, so it has to go to the left in this case. The magnetic field still goes out of the page, so you can see that the force ends up going upwards. So we know the direction goes upwards, we know the magnitude, so let's sub in everything to give us some kind of number. So that's my QV, dropping all the signs, and my B is given by that. And we get some number and we know it goes upwards. Pretty simple question really, but just to kind of see how all these different equations mash up together. This next part is a little more interesting. Describe qualitatively the subsequent motion of the electron. Of course, you notice that the magnetic force is perpendicular to my V at this moment. So you would imagine it goes in some kind of arc. In fact, an arc away from the wire because of the way the direction is. However, it doesn't form a full circle. And why is that? Let me get a bit more space. You have a wire down here. Current goes like that. And right now, you're going to describe out some kind of circle, sort of like that. Because your magnetic field is of a certain strength right here. However, as you move away from your wire, your magnetic field decreases. So from here, your radius of curvature decreases and you scribe out a bigger circle. So depending on how all these things play out, it may not even form a loop at all. It might just slowly curve away, wider and wider. But we have to work all that details out, and at this point, it suffices to say that it doesn't form a perfect circle because as you move away from the wire, you are going to have your force decrease over time. So just be aware that a charged particle only goes in uniform circular motion within a uniform magnetic field. And in the case of a wire, it doesn't provide a uniform magnetic field.